Thank you for the nice introduction. It is really an honor to be presenting here today. So I am from Chemistry Education Division at Miami University at Oxford. And besides our main research projects, chemistry education students, we work on additional cognate project where we design different teaching activities. So today I will be talking to you about a novel lab that I've designed to help students understand what chirality is. And students will be using liquid crystal to explore chirality. So if you will take a look at the lab manuals in organic chemistry, we will be able to see that most of the labs there can be classified as expository, also called traditional or verification labs. Students are given a very precise procedure which they have to follow step by step, and in the end, the lab manual basically tells them the result that they have to get. Students' goal is to verify the result. Not a lot of emphasis is placed on students thinking about the results of their experiments. On the other hand, guided inquiry experiments, they have predetermined but not specified outcome. Students are not told what they will get as a result of their experiment, so they have to discover it to themselves. They're still given a very precise procedure that they can follow. However, they don't know what they will see in the end of the lab experiment. So more learning occurs, more emphasis on students analyzing their results and thinking and making conclusions. So what do we want to accomplish in our undergraduate organic chemistry lab? We for sure want students to understand, to get an idea what science is. We want them to learn essential skills for their future scientific work. And as you know, when we do real science projects, we are never given the right answer. We always have this research question that we want to answer. So because of that, why do we teach students, giving them these traditional verification labs where students don't basically learn the skills? For this reason, we think that we should focus more on design of guided inquiry labs, open inquiry labs, problem-based labs. I'll be not talking about it today, but feel free to ask questions about those if you have. So this lab was designed more as a guided inquiry approach where students have to discover the concepts for themselves as the result of their lab. So why chirality? Even though chirality is introduced in multiple disciplines in physics and chemistry, students still find this concept really challenging. It's probably due to the fact that chirality is a very abstract concept. Chirality is normally highly covered in lectures and not so much in lab activities. When students learn about chirality in organic chemistry lab, it's normally experiments about resolution or polarimetry. And just think about it. When students do a polarimetry experiment, the result of their experiment is basically students are getting a negative or a positive number. Do really students connect to these numbers? Do these numbers make a lot of sense to students? We think that maybe we should design something that will be more obvious for students. So here we were working on a really simple way to help students visualize the manifestation of chirality with a naked eye. So the learning outcomes for this lab are the fact that students will be learning about very subtle abstract molecular concepts about chirality, and we will be using liquid crystals as a tool to help students investigate what chirality is. So our design was based on the principle of the color generation in doped pneumatic liquid crystals. As we know, when we add a chiral dope onto pneumatic liquid crystal, it will induce a chiral twist, and we will end up with cholesteric liquid crystal. Normally, these liquid crystalline phases, they reflect light at a particular wavelength. So why do we get this light? Just as our previous speaker was talking about, when we have incident light striking the cholesteric material, the polarized light with the same handedness will be reflected, whereas the polarized light with the opposite handedness will be transmitted to the material. In order to get cholesteric structures, we want our chiral dopant to have high helical twisting power. Helical twisting power is basically a property of chiral dopants to be able to induce a cholesteric twist in specific nematic liquid crystals. And on this slide, you can see an example of deoxylane dopant, and as you can see, it has higher helical twisting power with E7 because E7, the chiral dopant structurally resembles the E7. However, the helical twisting power with MBBA is much less than that. So our work was inspired by work of Professor Ben Feringa. He and with his coworkers, they designed a very simple visual test to predict the enantiomer purity of a synthetic mixture. For his system, they were using a chiral amine that they mixed with carboxylaldehyde to get this imine chiral dopant. And after that, they mixed the imine chiral dopant with E7 liquid crystal. Basically, they prepared different mixtures with different percent EE of 100, 90, 70, 60, and 50% EE. And based on that, their mixtures gave different colors, starting from red to purple, thus covering the entire spectrum of visible light. So, as I said, we were really inspired by his work, and we decided to adopt the system reported in Feringa's paper and to use it for our experiment design. However, we decided to modify the system because when somebody is designing an experiment, the person should really think about having all materials really inexpensive or easily synthesized and commercially available, because you will be doing this lab with a lot of students, so it means that you will have to buy a lot of materials, and universities cannot afford very expensive chemicals. Because of that, we decided to modify the chiral dopant. We got rid of this with this methoxy group because the carboxylaldehyde used to synthesize this chiral dopant is more expensive when it contains this methoxy group. And also, we instead of E7, we were using mixture of MBBA and EBBA liquid crystals. So this lab was piloted with 10 graduate students in the beginning of the spring. And after that, in April, it was successfully performed by 84 organic chemistry majors at Miami University. So the lab itself contains from two main parts. In the first part, students are synthesizing their chiral dopant. In order to synthesize the chiral dopant, they start with a chiral amine. They add to it a carboxylaldehyde, and they get this chiral dopant. As you can see, the configuration of the chiral dopant depends on what was the starting amine, R or S. However, students were not told what was their amine. It was their unknown. We gave it to them. We never told them. So that was the big question that they had to solve in the end of their lab. They had to understand what was the stereochemistry of their final product. So the synthesis was performed by first students heated their reactants at reflux for 15 minutes. After that, they performed vacuum filtration of their product, and after that, they characterized their product by obtaining its melting point and infrared spectra. So as you can see, a very simple way to synthesize the chiral dopant. That is something we were aiming for, to make it quick and simple so that all students can do it. In the second part of the experiment, students were using the chiral dopants that they synthesized in the first part, and remember, they didn't know either it's R or S chiral dopant. And they were mixing the chiral dopant with a mixture of MBBA and EBBA liquid crystals. After stirring this mixture, they were getting this kind of opalescent, multicolored, slightly multicolored mixtures. After that, they were asked to place one drop of their mixture on a glass slide and cover it with a cover slip. As you can see, when not touching, here I'm not touching, my finger is above the cover slip. I'm talking about the first picture. When not touching, the cover slip looked completely transparent. However, with a slight touch and when students start shearing a little bit the glass slide, they saw kind of not just like a color generated, they saw it like being a little bit sparkly, very shimmery, opalescent, and so basically while they were shearing, they were forcing a planar alignment of the molecules, and because of that, they saw a color in the form of selective reflection of light. After doing this part, students were also asked to heat their glass slides, and most of the time they will get the mixtures with a permanent color. They don't have to shear it in order to actually get the color. So as you can see on this slide, there is a S mixture of the chiral dopant with MBBA and EBBA. And here is the same chiral dopant, but the same mixture, but the picture is taken through different circular polarizers, through the left and through the right. It's the same mixture. As you can see that the color is transmitted only through the left lens, and nothing can be seen through the right lens. So in our lab, instead of using just the circular polarizers, we decided to use 3D glasses because we wanted to give students something that they use in their everyday life so that they can learn also how 3D glasses work. And hopefully now when they will be going to watch 3D movies, they will be thinking, oh, I've learned something. Oh, that was this awesome lab that I did, hopefully. So as you can see on this picture, there is another S mixture, but it's the same mixture through both of the lenses of 3D glasses. It's not two different glass slides. As you can see, students could see the mixture only through the left lens of the 3D glasses, just like here, and not through the right. Opposite observations students could make for the R mixture, where the light was transmitted only through the right polarizer, circular polarizer, and not through the left. After doing this part, we gave students unknown glass slides with similar mixtures, but we told them which glass slide is what, whether it's R or S. And we asked students to calibrate the lenses in their 3D glasses. So they were able to understand which lens is responsible for which enantiomeric mixture. And once they calibrated their 3D glasses, they could actually find out to themselves what was that starting amine that they were getting, the chiral amine, in order to prepare the chiral dopant. Also, after students performed these observations, we asked them to figure out how to prepare a racemic mixture. And for that, they just simply had to mix equal amounts of the R chiral dopant, S chiral dopant, mix it with MBBA, EBBA, go through the same procedure, through the same observations, and as you can probably predict, they could not see any color generation through either lenses of 3D glasses. And in our post-lab questions, we asked them questions to make connection, why they see color in one case and why they don't see color in the other case. So, as I said, besides helping students understand what chirality is, and we also wanted them to understand a little bit, to get a little bit of knowledge about liquid crystals, because as we know, liquid crystals are very technologically important state of matter. However, it's not covered in undergraduate courses at all. So we gave students the structure of MBBA in their student guides, and we told them that liquid crystals are intermediate state between solids and isotropic liquids, and we introduced them to the fact that besides melting temperature, liquid crystals also have a clearing point. However, we thought that just saying this is not enough for students to stick to the idea. So because of that, we actually asked them to determine the melting and clearing temperature for the EBBA liquid crystal. So they were using a simple melt temp apparatus, which is in every organic chemistry teaching lab. So students started with a solid, and then they heated it. They saw a transition to a non-transparent fluid. And after that, after heating even more, they saw that the fluid changed and it became a transparent isotropic liquid. So hopefully in this way, once they could kind of visualize this to themselves, they could better connect to the idea. And yes, we would really love them to see the liquid crystals under polarized microscopes because their textures are amazing. However, we cannot do that because not all teaching organic chemistry labs have polarized microscopes. Actually, none of them have. So, and we don't think that any lab would like to purchase those to help students learn about liquid crystals. So this lab is very easy to be implemented because it does not require any special equipment. All equipment used is traditional equipment that can be found in any teaching organic chemistry lab, except for you just need to buy additionally 3D glasses and glass slides. Besides this experiment can be easily incorporated with polarimetry and recrystallization experiments. For example, like recrystallization of chiral amines with tartaric acid. This experiment will work perfectly well for both first and second semester organic chemistry students, for majors and non-majors. So I would like to thank Miami University undergraduate students who did this lab and instructor of the course, and the graduate students from Hartley, Bretz, and Izersky research groups who helped me, who did the pilot run of this lab. And thank you very much for your attention, and at this point I will be happy to take questions.
So when you say that chemistry lab does not have polarizing microscope, do they have ordinary microscope?
No. Like I can say about the teaching organic chemistry lab in my university, it's not normal research lab, it's a teaching lab, right? So normally teaching labs, they don't have microscopes, or if they do, those microscopes are not polarized microscopes.
Yeah, that's my question. You simply can put two polarizers in your microscope, it would be polarizing microscope.
Yeah, it's easy to do. We don't argue with that, but remember that the main focus of this lab is to help students understand chirality. So that was the major part of their experiment. We just wanted to, they use liquid crystals as a tool to investigate chirality. So we wanted kind of to give them a more like idea of what liquid crystals are on a very general, basic way.
I would say that a very small fraction of organic chemistry teaching labs have microscopes. It's just not a normal thing that you would have. So that you probably have 10 or 15 going in parallel. You have to have a microscope for every lab.
But when you get something, how you can establish what you got?
You already
You synthesize something.
You don't use a microscope.
So
What's
what's
a little too small?
Physicists want to solve this problem by building microscopes. But my question is there a way is there a way to assess the superiority of this approach over the conventional approach which you crossed out? I mean, do you have a way of assessing the effectiveness of this particular scheme?
What do you mean? I didn't
Can you measure how well the students learn about molecular chirality as compared to not doing it?
Well, we don't give them post-assessments, right? We just give them post-questions where they have to analyze the results that they obtained in the lab. But I cannot say for sure how much they've learned. However, we know that with this kind of approach, with guided inquiry approach, like in chemistry education division, we read a lot of literature. So we know that studies show that verification labs are not as effective. However, students really learn. More meaningful learning occurs when they do this kind of guided inquiry labs where they have to discover something for themselves. And with this lab, students, they didn't expect like what they will see. And they really saw this like sparkling color, very shimmery color. And for them, it was like, whoa, like I heard a lot of like students being very surprised by what they saw. So hopefully this kind of promoted them to think what is happening? Why is it happening this way? I don't understand. And we help with our post-lab questions. We try to help them make these connections between why they see what they see.
I think this is an amazing tool for a number of students.
Thank you.
And my question is whether you thought to expand it not just to organics chemistry students, but to material students, because that to me is a very clear connection to the optical properties of a number of materials.
Actually, I didn't, because this was my cognate project. I have my main project. So plus my cognate area is organic chemistries, and we don't have materials course for undergraduate students in my university. Maybe I'll think about it, but I don't think my other advisor will let me spend time on something else. Now it's time to focus only on my major research project.
I have one more comment that I feel compelled to mention, which is that for the physicists out there, you can't get a real racemate by weighing out equal quantities of 2 enantiomers and mixing them. There's probably 100 wrong papers in the literature where people tried this. A real racemate is like 1 part in 10 to the 10 of excess of 1 of the enantiomers if you have a gram of stuff. So you can't get close to that by weighing, but for the students, I think actually weighing the enantiomers and getting something that's like a racemate works for the students because it emphasizes what a racemate is.
Yes, we were.
But it's not really a racemate.
We were a little bit worried about what if students will be not as precise with their measurements. What if they will still see a little bit of color generation because they will have more of one enantiomer than the other. However, I did some tests before students actually did it. I made mixtures of different EE, like 5%, and you don't get the color right away. So even if they are not very precise, they will still not see any color generation. So.
But still, if you're going to try to do an experiment mixing enantiomers to get a racemate, you're going to see parity violation. And you're going to publish that, and it's going to be embarrassing.
That's true for commercial racemates, too.
Yeah, absolutely true. Right. You buy a racemate from Aldrich, it's not necessarily racemic. So you got to be really careful. Well, let's thank Maia.
Thank you.